magnetic field induction at a point on the axis of a current carrying circular coil. Magnetic field at a point on the axis of a current carrying circular coil, that is on the axis of a circular coil carrying current I. This is a circular coil and we can draw the axis of the coil which is perpendicular to the plane of the coil. A is the radius of this circular coil. Current flows downwards in front portion of the coil and current flows upwards in the back portion of the coil. O is the center of the coil and we can consider a point P on the axial line or on the axis of this circular coil. We can consider a point O1. At the upper edge of the coil, and another point is O2 at the lower edge of the coil. O1 and O2 are the 2 diametrically opposite points. We can consider a small element A1C1 of length dl around the point O2. 1p is the oblique distance of the point P. dl is the length of the small element A1C1. Similarly, we can consider another small element A2C2 at the lower edge of the coil, and dl is the length of this small element A2C2. We can connect the 2 points O2 and P. O2P is the oblique distance of the point P, and here x is the distance of the point P from the center O. R is the oblique distance of the point P. We can extend the axis OP up to x, that means, and also we can draw y-axis. Now we can write what? Let us consider two small elements. A1C1 and A2C2 of length dl. Let us consider two small elements A1C1 and A2C2. Two small elements A1C1 and A2C2. Let us consider two small elements A1C1 and A2C2 of length dl of the coil at the 2 points O1, O2, at the 2 points O1 and O2, which are situated at diametrically opposite edges of the circular coil carrying current I. Now the magnetic field induction at P due to the current element A1C1 will be acting along the direction pK1. dB is the magnetic field induction at the P on the axis of the circular coil due to the current element A1C1, and this magnetic field dB acts along a direction pK1 at right angle to the oblique distance r of the point P. So here we can consider that at the point P magnetic field induction dB acts along pK1, and this magnetic field induction dB acts at a right angle to the oblique distance vector r of the point P from the circular coil. According to Biot-Savart law, the magnetic field induction at the point P due to the current element A1C1 or I vector dl, that is due to the small element A1C1 at the point O on the circular coil is given by dB equal mu0 by 4 pi ideal sine theta divided by r square. Ideal sine theta divided by r square, where theta is the angle subtended by, where ideal is a current element. Ideal is the current element. Where vector dB acts at right angle to the plane, in which small length vector, that is vector dl, and oblique distance vector r act. Vector dB acts at right angle to the plane in which vector dl and vector r act. Now if we draw a conductor xy carrying current I, here we can draw a conductor xy carrying current I. O is a point on the conductor, dl is the length of small element, r is the oblique distance of the point P. From the conductor xy or from the point O, we can draw this tangent, and this tangent makes an angle theta with the oblique distance. At P, magnetic field induction acts inwards. Similarly, at O1 we can draw a tangent OT1. This tangent OT1 makes an angle theta equal 90 degree with the oblique distance r of the point P from the coil. The tangent OT1 on the current element A1C1 makes an angle theta which is equal to 90 degree with the oblique distance r. Here vector dl, that means length vector of the element A1C1, is perpendicular to vector r, hence theta equal 90 degree. Therefore dB equal mu 0 by 4 pi ideal sine 90 degree divided by r square. Therefore dB equal mu 0 divided by 4 pi ideal by r square. We get the expression of magnetic field induction, that is dB equal mu 0 by 4 pi ideal by r square. This is the magnetic field induction. At the point P due to the current element A1C1 at the edge O1 of the circular coil. Now vector dB has the expression mu 0 by 4 pi I vector dl cross vector r divided by r cube. According to the property of cross product between two vectors, this angle is theta, which is 90 degree. According to the property of cross product, vector dB is equal to mu 0 by 4 pi I vector dl cross vector r divided by r cube. That's why vector dB is perpendicular to vector dl, and also vector dB is perpendicular to vector r. So dB equal mu 0 by 4 pi ideal by r square, which is the magnetic field induction at the point P on the axis of a circular coil, carrying current I. Magnetic field induction at the point P on the axis of the circular coil due to the current element I vector dl, that is due to the small element A1C1. The magnetic field induction dB acts at an angle phi with the y-axis. We can draw the tangent O1T1. The tangent O1T1 makes an angle theta equal 90 degree with the oblique distance. Taking dB as the diagonal, we can draw a rectangle to resolve the magnetic field induction dB. Now the horizontal component of the magnetic field induction dB along x-axis is dBsinθ. The horizontal rectangular component of dB along x-axis is dBsinθ, and the rectangular component of the magnetic field induction dB along y-axis or in vertical direction, the rectangular component of magnetic field induction dB is dBcosθ. Similarly, we can consider the current element A2C2 at O2, that means at the lower edge of the coil. A2C2 is another current element of length dl, and due to this current element A2C2, magnetic field induction at the point P on the axis of the circular coil of radius A will act along the direction pk2 such that this magnetic field induction will be acting at right angle to the distance vector r, which is equal to O2P. We can denote. Similarly, we can draw a rectangle to find the direction of magnetic field dB due to the current element A2C2 at O2, that is at the lower edge of the circular coil. This is an imaginary rectangle, and along this diagonal PK2, magnetic field induction dB prime due to the current element A2C2 at the lower edge O2 of the circular coil will be acting. dB prime is the magnetic field induction which is acting along the direction PK2 due to the current element A2C2. This magnetic field induction dB prime acts at right angle to the distance vector r. In that case, if we consider the current element A2C2 of length dl, similarly the magnetic field induction at the point P due to the current element I vector dl, that is due to the small element A2C2 at the point O2, is given by dB prime equal mu 0 by 4 pi I dl sin theta divided by r square. Now theta is the angle subtended by the tangent OT2 at the point O2 with the distance vector r. We can draw a tangent at the point O2. O2T2 is the tangent which makes an angle theta equal 90 degree with vector r. That's why dB prime is equal mu 0 by 4 pi I dl by r square. Since theta equal 90 degree, dB prime is equal mu 0 by 4 pi I dl by r square. dB prime is equal mu 0 by 4 pi I dl by r square, where theta equal 90 degree. Therefore, dB prime is equal dB. That means magnetic field induction at P on the axial line of the coil due to the current element A2C2 and A1C1 are same. And this magnetic field induction dB prime acts along the direction PK2. Similarly, we can assume that the magnetic field induction dB prime acts at an angle phi with the negative y-axis. The magnetic field induction dB prime acts at an angle phi with the negative y-axis, and we can find the two rectangular components of dB prime. Now, the rectangular component of the magnetic field induction dB prime along negative y-axis is dB prime cos phi, and the rectangular component of the magnetic field induction dB prime along the axis is dB prime sin phi. The rectangular components of dB and dB prime along y-axis, that is dB cos phi and dB prime cos phi cancel each other, but the rectangular components of dB and dB prime along x-axis, that is along the axis of the circular coil, will be added. The rectangular components of dB and dB prime along x-axis or along the axis of the circular coil, that is dB sin phi and dB prime sin phi, will be added because they are acting along the same direction. but dB prime cos phi and dB cos phi cancel each other because they are acting in the opposite direction. Hence the total magnetic field induction, that is the magnetic flux density, the total magnetic field induction, that is magnetic flux density at the point P due to the current element through the whole circular coil is given by B equal integration what? It should be integration dBsinθ phi or integration 2 dBsinθ phi. We have already considered two current elements, A1 C1 at O1 and A2 C2 at O2, and magnetic field induction along the axis are dBsinθ phi and dB'sinθ phi due to these two small current elements. That's why the expression of magnetic field induction B will be what? Which one is correct? Integration dBsinθ phi or integration 2 dBsinθ phi? As we consider the whole conductor or entire portion of the circular coil, that's why we have to consider that the total magnetic field induction B at the point P will be what? Only integration dBsinθ phi. That means that is the summation of magnetic field induction due to n number of elements on this circular coil due to one current element two current elements B equal dBsinθ phi plus dB'sinθ phi. But due to n number of current elements B equal dBsinθ phi plus dB'sinθ phi plus plus dB''sinθ phi plus that is equal to integration dBsinθ phi, not the integration to dBsinθ phi. It should be B as equal integration dBsinθ phi equal integration mu 0 by 4 pi I dl by r square sin phi. Now we can bring the constant terms outside integration, that is bringing mu 0 by 4 pi I sin phi by r square outside integration, and we get B equal mu 0 by 4 pi I by r square sin phi integration dl equal mu 0 by 4 pi I by r square sin phi. Integration dl is equal to the circumference of the circular coil, which is 2 pi a, where dl equal 2 pi a, which is the circumference of the circular coil of radius a. Integration dl equal 2 pi a, which is the circumference of the coil, and a is the radius of the coil. So finally we get B as equal mu 0 by 4 pi I by r square sin phi 2 pi a. Now we can denote the angle subtended by the oblique distance r with the axis OP, that is phi. Phi is also the angle subtended by the oblique distance r with x. Now we can denote the angle subtended by the oblique distance r with y-axis as psi. This is the angle psi, and that angle is phi already we have assumed. So as O1P is perpendicular to PK1, that's why psi plus phi is equal 90 degree. And also the axis OP is perpendicular to y-axis, that's why psi plus phi prime equal 90 degree. Psi plus phi prime equal 90 degree. That's why as both are sum of that two angles is 90 degree, that's why we can assume that two angles as phi, or comma B equal mu 0 by 4 pi I by r square. In place of sin phi we can write O1 by O1P by O1P, perpendicular by hypotenuse from that triangle O1OP. O1 divided by O1P dot 2 pi a, or comma B equal mu 0 divided by 4 pi I by r square dot a by r dot 2 pi a, or comma B equal mu 0 by 4 pi I by r cube dot a square dot 2 pi I by r cube dot a square dot 2 pi. Therefore b equal mu 0 I a square divided by 2r cube, where r equal to root over a square plus x square in the diagram. B equal mu 0 I a square divided by 2 under bracket root over a square plus x square whole to the power 3. So finally we get b as equal mu 0 I a square divided by 2 bracket open a square plus x square whole to the power 3 by 2. B is equal mu 0 I a square divided by 2 a square plus x square whole to the power 3 by 2, which is the magnetic field induction at the point P on the axis of the circular coil having only 1 turn. If there are n number of turns in the coil, in that case what should be the expression of magnetic field induction B? B will be equal to mu 0 n I a square divided by 2a square plus x square whole to the power 3 by 2. So this is the magnetic field induction. At the point P. On the axis of a current carrying circular coil. B equal mu 0 n I a square divided by 2 a square plus x square whole to the power 3 by 2. This is the magnetic field induction at the point P on the axis of the current carrying circular coil of radius a. And this magnetic field induction acts along the axis and away from the coil. So we can draw a circular coil carrying current I. Current flows in this way as shown in the figure. This is the front side of the coil and that is the back side of the coil, and through the back side current is flowing upwards. O is the center of the coil having radius a. Small a is the radius, and we can draw the axis OP which is perpendicular to the plane of the coil. X is the distance of the point P. At the point P, magnetic field induction B acts along x-axis. Magnetic field induction as the expression B equal mu 0 n I a square divided by 2 a square plus x square whole to the power 3 by 2. Now we can consider this current carrying circular coil with a charged ring. This is a charged ring, and a charge plus q is uniformly distributed along the circumference of this ring. We can draw the axis of the ring. OP is the axis of the ring, and the point P is at a distance x from the ring. A is the radius of the charged ring. If unit positive charge, that is +1 charge, is placed at the point P on the axis, in that case electric field intensity at the point P will be E. And here this is the charged ring, and electric field intensity at the point P, that is the electrostatic force experienced by unit positive charge at P, is E, and the expression of E is equal 1 by 4 pi epsilon 0 q dot x divided by a square plus x square bracket close whole to the power 3 by 2. E equal 1 by 4 pi epsilon 0 q dot x divided by a square plus x square whole to the power 3 by 2. So for a small charge ring, the radius a is 0, and we can find E as 1 by 4 pi epsilon 0 q divided by x square, that is the electric field intensity due to a point charge. When a charge ring is very small, that charge of the ring behaves as a point charge, and this electric field intensity E due to a charged ring it can be compared with the magnetic field induction at the point P on the axial line of the current carrying circular coil. E has the expression 1 by 4 pi epsilon 0 q x divided by a square plus x square whole to the power 3 by 2. In this case we have q dot x, that means product of charge into the distance of the point P, but for B it is mu 0 n I a square divided by 2 a square plus x square whole to the power 3 by 2. 2.